So this is that index of refraction, right? And it's just light slowing down in some medium. So what we can do with this is let's pretend we have let's look at a soap bubble. Okay, a soap bubble is a good thing to look at for this. For the soap bubble, what we have is we have a region, we'll call it N1, and this is air. So its index of refraction equals 1. And then this right here, I guess I'll make it a little bit of blue. This is the bubble. So I'll call this N2. It's the bub. It has an index of refraction of, let's just say like 1.5. I don't know off the top of my head what the index of refraction of a bubble is. Let's just pretend together that it's 1.5. Okay? And then once you go through the bubble film, you get to the inside of the bubble, and trapped on the inside of the bubble, we'll call this N3. It is air. Its index of refraction just equals 1. Now, there is, I don't want that. There's a sweet demo from Penn State, which is going to make good use of what we're talking about. And there's also a good PhET lab. Maybe you've done PhET labs, maybe you haven't. Called Waves on a String. If you give me a second, I'll pull it up real quick. But essentially what's going to happen here is as this light wave comes down and it strikes both the air bubble on the outside, so the bubble surface, and then it passes through and it strikes the back of the bubble, we're going to get what's known as a hard and a soft reflection. So, boom, do that. I want no damping. So if I have a fixed end here and I send a wave pulse through, then what's going to happen is you see it's going across this, like up top, and when it hits the side that's clamped down, it turns over. That's a hard reflection there. That hard reflection gives it a half of a wavelength change. So it turns something from going to the top side, like the crest of a sine wave, into the trough of a sine wave. So that's a phase shift there. It's a change in the phase of the sine or the wave function by a half of a wavelength. We can think of that as pi radians or 180 degrees. Now, if I give it a loose end, notice the string or this little ring here floats up, and then if it's on the bottom side, it floats down. Okay? Whenever it sends that wave pulse back, it stays on the same side. And since it's staying on the same side, we call that a soft reflection. There's no change in the phase of the wave there. It doesn't shift at all. It's staying up top and ending up top. It's staying down below and it's ending down below. So there's no phase change there. Since there's no phase change, the light's just going to keep traveling however it was. So what we can do with this is we can look at our scenario and ask ourselves, okay, how is the light traveling here? So what's occurring for a beam of monochromatic coherent light is it's technically coming directly down. It's technically coming down, striking the bubble surface. Some of that light is going back up. Some of the light is going through to the bottom. When it bounces at that boundary layer where the indexes change, some of it goes back up and all the way out, and some of it goes through. That looks really silly to look at, so let's not look at it like that. Let's just do this. Let's understand that what we are looking at right here, we are looking at light coming straight down, entirely perpendicular to the surface, so we don't have any Snell's law nonsense. But let's draw it at an angle so we can actually see what is going on. When the light comes down, it strikes the surface, and some of this light is reflected out. Some of this light is transmitted through and then reflected out. That light that's transmitted through and then reflected out, it had to go through an extra distance, which is twice the thickness of the bubble, or for your lab, twice the thickness of the air gap in between a glass plate, air, and a glass plate. Okay, so it's the same idea. It's the same idea of a thin film here, but it's glass, air, glass. So yours would be like, here's glass, here's air, here's glass. Okay? Now, this distance that this second piece had to go through, I'll draw it in red real quick. This extra distance it had to go through was twice the thickness of that air gap. No, Sheen, I don't want any wings, man. I'm good. Maybe one. Well, it depends what types of wings. No, I don't need any wings. I'm doing stuff tomorrow. I eat wings. Ugh. Tummy will be all everywhere, and I'll get all sick. But I do appreciate it. I do appreciate the offer of wings. Check it out, Sheen. We're doing thin films for a header. They're in Canada, and they're just getting into optics. So anyways, that light that passes through into that air gap has to go through some air gap thickness, or the bubble thickness, depending on how you think of it, and it's twice the thickness of that gap because it has to go down through it, bounce off the back, and then come back up. This thickness here, that's the thickness of the hair you're looking for. That's your lab. Well, other than the thickness of the hair having to be traveled through, we also have a possibility of a phase change due to that shift. So we have a phase shift due to the reflections. So we have a reflection here and here. We're going to call this path up here delta A, and we're going to call the path down here delta B. Okay? If we're looking at an air, a bubble, and then air, then right here I have a hard reflection because I'm going from a low index to a high index. Since that's a hard reflection, I am shifted by half of a wavelength, lambda over 2. For delta B, the change in path length for the bottom light, well, it already has 2 times the thickness to go through. I mean, it had to move down through the film and then out through the film. But it also may have a reflection. So if we look at this, well, we're going from a high index, 1.5, to a low index, 1. Well, that's a soft reflection there. We don't have any extra phase change. So this is just nothing. The path length difference that we care about, delta L, and this is a similar idea to the double slit where it's that path length difference causes this change here, and it causes that light to either be in phase or out of phase. Well, that path length difference is just delta B minus delta A. So what we see here is we'll see 2t minus lambda over 2. So we see 2t minus lambda over 2. And this has to be equal to get a bright spot, similar to the double slit. To get a bright spot, it has to be equal to m lambda. because we know for both the double slit and the thin film, if our light is in coherence again, we are going to get a bright spot out of this. So at this point, it's just a matter of solving this for the thickness of the hair you want. We'll add lambda over 2 to the other side. Doing so, we get, oops, we get a new page. We get 2t equaling, and then I'm going to put this together. I'm going to pull out a like term. I'm going to get m plus 1/2 lambda, because that's like m lambda plus lambda over 2, so I pulled a lambda out. And when I do this, I now have to choose for myself, okay, what is my value of m? In this case here, traditionally, we want to choose the smallest value of m possible without turning the entire right side of the equation equal to 0. Because if the entire right side of the equation is equal to 0, that means 2 times the thickness of your hair equals nothing. And that means the thickness of your hair equals nothing. But you clearly have thickness to your hair. So the smallest value of m on the right side we could pick here, while still having stuff on the right side for our case right now, is m equals 0. So that just leaves us with t equals, or 2t equals lambda over 2, which is that the thickness equals lambda over 4. Okay, so that's how you can find the thickness of a soap bubble. For the hair, it's a similar idea, but you're going from glass to air to glass. This is an index of like 1.3 to 1 to 1.3. So you're going to have a soft reflection, and then you're going to have a hard reflection there. So it's a little bit different than this, but it's a very similar setup. Either way, you'll know you did the problem at least close, if not completely right, if your answer is either t equals lambda over 4 or t equals lambda over 2. One of those answers has to be correct. In our bubble scenario here, this gave us the bright spot. That means this is going to give us the dark. That doesn't always need to hold true with lambda over 2 is the dark. There are scenarios, depending on how you have a reflection, hard or soft, and the order, maybe hard, hard, maybe soft, soft, maybe soft, hard, maybe hard, soft, whatever, that the lambda over 2 could be the bright spot. It just depends what you have. You just need to work through it each and every time. But no matter what, these will be your 2 answers. You know it's either going to be lambda over 2 or lambda over 4. It's just a matter of which one is it. The other thing to point out here, and this is a very subtle piece, and it won't really apply to your specific lab, but I'd like to cover it just in case. These lambdas here, these are what I refer to as lambda propers. That is the wavelength in a vacuum. The wavelength you're actually looking at, though, for that thickness, it's the wavelength inside the film, whatever that film is. For our bubble scenario, that wavelength changed because it was in something with a higher index of refraction. So what you'd have to do is you'd have to say, like, look, this wavelength we actually care about over here, this lambda, it's actually the lambda proper. It's the wavelength of whatever our laser says it is, divided by the index of refraction of the film itself. For your hair lab, you won't need to worry about that because your film is air. And we generally say that the index of refraction of air is equal to 1. So you won't have to worry about that as much, but it is something to be aware of when you're doing that. Okay? So that's how I think your teacher wants you to do this. That's how I would expect my students to do it. It's a neat one, but it is one that can be done. But it's a thin film. It's not exactly a double slit. My guess is that if you haven't done that hair lab yet, or if you haven't gotten to thin films, they'll be teaching that to you in the next day or two, and That's what you're probably supposed to be using for that lab there. Okay. That help you out, Header? I hope that helped you out. Well, thanks for the follow. That was always helpful. What just happened? Something just happened. Oh boy, look at that. Look at all those cheers. I think that's the first time it's ever happened. That's awesome. Thank you so much. I got a sound going off, and I was like, what the heck is that? It's never happened before. Yeah, I hope that helped. If you look in your textbook, you said you're using Nelson Physics 12. Like, what you're looking for is thin film interference for that. So that's an important thing there. Okay. And if you are taking like the IB test or the AP Physics 2 test, like that's something that pops up enough to make it something that we need to teach. It doesn't pop up too often. But if you see a multiple choice question and there's like 4 answers there, one of the answers to, you know, how thick is that film, it's either going to be T over 4 or T over 2. And if you don't want to solve that out because you're like, I'm running out of time, you've got a 50-50 shot at least. And that's what I tell my students. It's always going to be either T over 4 or T over 2. So that's how I think about that. And, you know, check out those links. Those links are helpful too. The thin film problem, I walk through another one of these, just kind of like with the air and bubble or the glass and the air and the glass. But I do it with air, oil, and then a wall, which has like an index of infinity. So I walk through that problem. It's a problem I give to my students.